So where we left off on Tuesday's lecture was talking about electron configuration. So where the electrons go, okay, how they march is something that we're interested in. So first they'll go to 1s. First they'll go to the 1s orbital. So we'll call this 1s here. Okay, so that would be 1s1. And then what would be the next one? Okay, so that's 1s1. Okay, 1s2. And then after filling the 1s orbital, where will they go? They'll go to 2s, and then after that, where will they go? 2p, 2p1, 2p2, 2p3, 2p4, 2p5, 2p6. After 2p, where will they go? 3s, 3s1, 3s2. After 3s, where will they go? 3p, 3p1, 3p2, 3p3, 3p4, 3p5, 3p6. Okay, so we have the filled shell here. After filling n equals 3, where will they go? 4s. Very good. 4s1, 4s2. After filling 4s, where will they go? Okay, so 3d. 3d. This is known as the n-1 block. Okay, also known as the transition metals. Right here. Right, after filling the 3D, where will they go? 4p, 4p1, 4p2, 4p3, 4p4, 4p5, 4p6. We have a filled n equals 4 shell. Yes or no? Yes? Yes. Okay, after filling 4s, 3d, 4p, where will they go? 5s. Okay, 5s1, 5s2. After 5s, where will they go? 4d. Okay, they'll go to 4d. Okay, after 4d, where will they fill? 5p. 5p1, 5p2, 5p3, 5p4, 5p5, 5p6. A filled n equals 5 shell. After 5p, where will they go? 6s. Okay, 6s. After 6s, where will they go? Okay, they will go to 4f. This is the n-2 block. The n-2 block. Okay, also known as the lanthanides and actinides. Lanthanides, which are at the top, and the actinides, which are at the bottom. Okay. 4f1, 4f2, 4f3, 4f4, 4f5, 4f6, 4f7, 4f8, 4f9, 4f10, 4f11, 4f12, 4f13, 4f14. After 4f14, where will it go? Okay, very good, Gerardo. 5d. After 5d, where will it go? 6p. 6p1, 6p2, 6p3, 6p4, 6p5, 6p6. This is a filled n equals 6 shell. After 6p, where will it go? Down to 7s. After 7s, where will the electron start filling? Okay, 5f. 5f1, 5f2, 5f3, 5f4, 5f5, all the way to 5f14. After 5f14, where will they go? Transition metals 6d. 6d. And then after 6d, where will it fill? 7p. 7p. So that is the order in which the electrons go marching. Okay, shall we review again? Okay, where will the first electron go? 1s, and then 1s2, and then the third 2s. And then they start marching. They're going to march in a very specific order. After 2s, where will they go? 2p. After 2p, where will they go? 3s. After 3s, where will they go? 3p. Then what? Now we go to the transition metals, 3d. After 3d, 4p. After 4p, 5s. After 5s, 4d. Okay? After 4d, 5p. Okay, go ahead.
In the 7p layer, is it only going to be 3?
No, these are undiscovered elements. This is, if you look at the newer versions of the periodic table, they have elements for these.
Oh, all right.
Yeah, these have not, these are just newly discovered. Yeah. So if you look at the absolute latest version of the periodic table, they have elements that were discovered. These are actually man-made, I think, some of them, but yes. So it's still 7p. All right, after 6s, where will they fill? 5d. After 6s, where will they fill? Sorry, my mistake. After 6s, where will they fill? 4f. Okay, after 4f. Okay, remember f has 7. 1, 2, 3, 4, 5, 6, 7. Okay, the f orbital. And we didn't talk about the shape of it. And yeah. Okay, so after 6s, they fill 4f. After 4f, where will they go? 5d. After 5d, 6p. After 6p, 7s. After 7s, 5f. After 5f, 6d. And after 6d, 7p. That will be all we'll go over. Okay, so how many subshells are in an s orbital? Okay, they can fill 2 electrons. So one shell, or filling in 2 electrons. And how will they go? Spin up, spin down. Okay, what about a p orbital? How many? 3 in the subshells. And how will they go? Up, 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 spin down, spin down, spin down. That's p. Okay, how will the d orbitals? How many subshells? 5. And how will they fill? Spin up, spin up, spin up, spin up, spin up, and then what? Spin down, spin down, spin down, spin down, spin down. Okay. Finally, the f orbital, how will they fill up? Even though we won't talk about this as much. Spin up, 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 and then spin down, spin down, spin down, spin down, spin down, spin down, spin down. Total of 14 electrons in the f orbital. 4f or 5f. Okay, so this is how we want to, this is how they go in. Okay, so once you know this order, I should give you any element in the periodic table and you should be able to determine its electron configuration. Okay, any element, as long as you know the order in which they go and enter the orbitals. Okay. So, okay. So there's one more thing I want to talk to you guys about, and then we'll wrap up this chapter, and we'll do our review. We'll start our review for next Thursday's exam. All right. So we went all the way up to here, and okay. So we have a filled n equals 3 shell. If you remember, all the way back to the first week of class, we said group 17A, or group 7A, or group 17 are the halogens. And what charge would they like to be? Yes, they would like to be -1 charge. Okay? So let's take a look at chlorine. Okay, we can do fluorine or bromine or iodine. Okay? So if chlorine is -1, okay, so we'll do the electron configuration of chlorine, which is neon 3s2 3p5. Okay. Now let's do the electron configuration of Cl minus. Cl minus. What's the electron configuration of Cl minus? 3s2, 3p5. So what's the electron configuration of Cl minus? Okay, it has gained an electron. It has gained an electron. So what is its configuration?
3s2, 3p6.
Okay, so what other element is 3s2, 3p6? Argon. Okay. So you see here, why does chlorine like to be -1? Okay, because Cl minus is noble. Okay, noble to what? Okay, noble to the noble gas argon. Okay. So these are noble because they have a filled shell. Okay, helium has a filled n equals 1 shell. Neon has a filled n equals 2 shell. Argon has a filled n equals 3 shell. Krypton has a filled n equals 4 shell, on and on. So I'm going to say Cl minus and argon. I'm going to say Cl minus and argon. Cl minus and argon are isoelectric. Okay, it means same electron configuration. Cl minus and argon. Can you name anything else? Okay, this is why these like to be 9 minus 1. Okay, if F gains an electrons and becomes F minus, what is its electron configuration? Neon. Okay. If sodium becomes +1, because these like to be +1, what would it be isoelectric with? What? Na plus. What will it have the same number of electrons as? Neon is the right answer. So what is another isoelectron pair? Na plus and neon. Okay, what else can be isoelectric with the noble gas neon? Not fluorine, but F minus fluoride ion. Correct. Okay, anything else? How about O minus 2? Would that be isoelectric with neon, gaining 2 electrons? Yes, very good. Okay. Magnesium plus 2 would be isoelectric, yes, very good, with neon. Okay. Okay, so all of these are isoelectric. Let's circle them in the pen. Okay, can you guys list me any other things that are isoelectric with argon? Let's look at our periodic table. And how about K plus? Potassium ion. How about calcium plus 2? What is it isoelectric with? Argon. Okay. Anything else you can think of?
Is it sulfur -2 also?
Sulfide, S minus 2. That's correct. Okay, so you guys listed some isoelectric species with argon. So this is the reason why all the way in the first and second week of class we told you that this likes to be +1 and this likes to be +2. Okay, why is that? They can easily attain the status of a noble gas, filled valence shell. Okay, remember, these are the noble gases, and the shells are filled, completely and totally filled. So that's why these are also called inert gases, because they don't need to pick an electron, they don't need to remove an electron. They are inert, stable. So what did we guys say was isoelectric with argon? Cl minus. Can you guys list me a couple of more? S minus 2. Okay, we said K plus. And then we said calcium plus 2. Okay? So these are isoelectric to each other. Same electron configuration.
Question. So does that mean in the 4A group they can be either gaining 4 electron or lose 4 electron to be stable?
Which one?
Like in 4A, it's like carbon. You can gain 4, right, to gain neon.
No, carbon is very different. Carbon is carbon loves 4, but it doesn't mean that it gains 4 electrons, and it doesn't mean it gives off 4 electrons. So carbon is its own unique entity, Wusong. You take organic chemistry; it's entirely the study of carbon. Okay, so everything is carbon chemistry in organic. So it's different.
Silicon and other 4A elements.
Silicon can be plus 4. Yeah, silicon is more like a metalloid, so it can be plus 4.
They can also be minus 4, isn't it?
It can be plus 4. It can also be minus 4. Yeah, these are the metalloids are a little bit, have properties of both, metals and non-metals. Yeah, but usually we want to go with over here and these two. That's what we know for certain. Okay, that's a good question. This carbon has its own class called organic chemistry. Okay. All right. So right now for this class, let's focus on these two, and then these two, and the noble gases. Yeah. Okay. So a couple of things here. This is just a review. Make sure you know the order. And you want to know, okay, I think we went over this, but I'm going to go over it again. Okay, how will they go in the 1s orbital? Okay, spin up, spin down. How will they go in the 2s? Okay, and then 2p. Okay, and then they pair. This is called Hund's rule. Hund's rule. Okay. Okay, that's the most stable arrangement. And then this is the order once again in which they will march. 1s and then 2s, and then after 2s where will they go? 2p. After 2p where will they go? 3s. After 3s where will they go? 3p. And then where will they go? After 4s where will they go? This is the transition metals. Okay, after that, where will they go? 4p, 5s. After 5s, where will they go? 4d. Okay, 4d. We're talking about right here in the periodic table. 4d. Okay, after 4d, that's the transition metals. Where will they go? 5p. Now we're over here in the periodic table. Okay, after 5p, where will they go? 6s. Okay, after 6s, where will they go? 4f. Okay, now after 6s, they'll go 4f. Okay, we're right here in the periodic table. We will fill up the 4f orbital, and then where will they go? 5d. We're at this region of the transition metals. After 5d, where will they go? 6p. Okay, right here at the p block. The p block. Okay, and then the 7s, and then after 7s, where will they fill? 5f. We're right here as the electrons march in. After 5f, where will they fill? 6d. We're at this block, the d block, and then we go to the p block and finish it up. Okay. So that is the order. Once you know the order, I think it should be okay. So this is called the D block, transition metals. these are called the lanthanides and actinides. Lanthanides, actinides. Okay, this is called the P block. Okay, and then finally, last but not least, this is called the S block. Okay, this is the S block in the periodic table. Okay, group 1 and group 2, alkaline metals and alkaline earth metals. Alright, so that is the electron configuration. We can actually, in your table here, we have a list of all the electron configurations. So, I mean, I know it's hard to see and stuff, but your book has a table of all of them, so you can check that out. Everything is nice until we get to some exceptions. There are 2 exceptions here, copper and chromium. We'll go over that. We'll do this practice problem, and then we'll start reviewing for our exam. Okay. All right, so some exceptions to the rule. Exceptions. Everything is so nice, everything is so fine, until we get to copper, until we get to chromium. Okay? So let's figure out what's wrong with that. And then, so on the exam, I want you guys to know this. Oh, my water bottle. All right, let's do the electron configuration of copper. All right, so, okay, copper. How many electrons do we have to fill in copper? How many? 27, 28, 29, okay? 29 electrons, okay? So we're going to have to fill up 29 electrons. So let's go ahead and do the electron configuration of copper. And that is 29, right? 29 electrons. 28, 29, 29. Okay. So we need to fill 29 electrons. All right, so how will the electrons get filled? Okay, what will they fill first? Okay, 1s, and then after 1s, what will they fill? Very good. After 2s, what will they fill? 2p. After 2p, what will they fill? 3s. After 3s, what will they fill? Very good. 3p. After 3p, what will they fill? 4s. And after 4s, what will they fill? 3d. Okay? So what period is copper in? Period 4. And what block is copper in? It's in the 3d block, right? 3d block. All right, and we have 29 electrons. We have 29 electrons. All right, so you can count with me 29. Okay, ready? Here we go. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29. Okay, 29. So normally you would think the electron configuration of copper would be, what's 3s2, 3p6? Argon. So you would think normally this would be, let me just write it this way. It would be argon 4s2 3d9. Okay, so that's how we would think it would be. Okay, because 3s2 3p6 is argon. So argon 4s2 3d9. But actually what happens is that this happens totally by itself. Okay? So the energy level between 4s and 3d is very small. Okay, it's very small. So this actually, and this happens by itself, it's actually more stable. It's actually more stable when this just gets promoted to the 3d. So we have what's called a self-promotion to a filled 3d orbital. Okay, it happens by itself. Okay. Okay. So the actual, this is more thermodynamically stable. Okay, this is more stable when this electron just kicks off and goes here to 3d. It just kicks off by itself, okay, like that. Okay. By itself, it just shifts and moves itself up. So the most stable electron configuration of copper is actually 4s1 3d10. Okay. This is the more stable because it's a promotion to a filled 3d. A filled 3d is more stable than what this is. Okay, when you fill up the 3d, it's more stable. Okay, so it's a promotion to a filled 3d orbital. Okay, so that is copper. Okay, so what would you imagine silver to be? 47. Okay, but what would silver be? Okay, so we have 47 electrons. Okay, 36 go the way of krypton. And then what would its electron configuration be? 5s1, 5s1, 4d10. That's very good. 4d10. Okay, so this is a promotion to a filled 4d orbital because this is much more stable. This is much more energetically favorable. Finally, what do you guys think gold would be? Gold. Okay. So we have 79 electrons. 54 will go and march the same way as xenon. After xenon, what would it be? 6s2, but it's promoted. So it's going to be 6s1. Okay, we have a 4f14. And then where will it go? 5d10. 5d10. Okay, so this is a promotion to a filled 5d orbital. So that's how you do that. Now sometimes so this is me, I like doing it this way. I like, the principal quantum number 4, and then comes 5, and then comes 6. So I actually like doing it this way. Okay, but you can put this on the test, okay? Because 4 comes before 5, and 5 comes before 6. But anyways, or you can write this as AG 4D10 5S1. So just ordering it by the principal quantum number is something that you can or cannot do, but I'd like it this way. This is teacher's preference. All right, so that is copper. All right, now let's go into chromium. Okay, chromium. Chromium is also a little bit strange. So there's an exception for copper, and then there's an exception for chromium. So how many electrons do we have to fill up for chromium? How many? 24. Okay, we have to fill up 24 electrons for chromium. So let's go ahead and do that and see what we get. Okay, so this is going to be the electron configuration for chromium. So chromium is going to be 24, right? Okay, 24. Okay, so let's go ahead and do the exact same thing that we did before. Okay, but this time, instead of filling 29, we're going to fill 24. All right? Okay, so what's the first orbital? 1s. Then it will fill 2s. After 2s, okay, after 2p, okay, after 3s, after 3p, 4s, after 4s, 3d. Okay, where's chromium at? Chromium is at 1, 2, 3. Period 4, it's in the 3d block. Period 4, 3D block, 24 electrons. Okay, let's go ahead and count them out. Okay, ready? Okay, here we go. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So what is 3s23p6 here? Okay, that's argon. So you would think copper would be argon, which is 3s23p6. It would be 4s2 3d4. Okay, that is not what happens. It's more energetically favorable because the energy gap between the 4s orbital and 3d orbital is very small, so it does a self-promotion. So it self-promotes so that you have a half-filled 3d orbital. Half-filled. Okay. We're talking about chromium. So this is not the right electron configuration. So what happens is that one of these electrons self-promotes. It just happens by itself. It self-promotes to a half-filled 3d orbital. So the right electron configuration for chromium is argon 4s1 3d5. Okay, now I like doing it in order of the principal quantum number, but both of these are right. Okay. So you can do this or this on the exam, that's fine. And this is a promotion to a half-filled 3D orbital. This is much more stable than that. Okay, this has more energetic stability than this. Okay, it's just more energetically stable.
Is it like these without transition metals?
Just with copper and chromium.
Or just copper?
The self-promotion, okay, happens by itself. You don't need to put any energy. The electron will just move itself from 4s to 3d to half fill this. Okay, the electron will move itself from 4s to 3d to completely fill this by itself. It's more stable that way.
And we also did it with gold, right?
Yeah, anything below copper and chromium.
Oh, or
Those two columns, right?
Those two columns. Yep, that's right. Yeah.
Do you have an extra periodic table?
Yeah, I have it in my office.
Like,
Yeah. Okay. All right, so having said that, what would be the electron configuration of molybdenum? 42. Okay, 42. Okay, 36 go the way of krypton. Okay, and then what would it be? Krypton. Okay, what would it be then? Krypton, 5s2, 4d5. Okay, promotion to a half-filled 4d orbital. Okay, 5s1, 4d5. Or you can write it in the order of the principal quantum number. Okay. So this is a promotion to a half-filled 4d orbital. All right, and below molybdenum would be tungsten. What would the electron configuration for tungsten be? Okay, we have 74 electrons. Okay, 54 will go the way of xenon. Okay. And then what would the electron configuration be? Xenon, 6s1, 5f4, 6s1, I'm sorry, 6s1, 4f14, 5d5. This is promotion to a half-filled 5d orbital. Okay, so you can also do it this way, making it 4, 5, 6 in the order of the principal quantum number. All right, like I said, this is a promotion to a half-filled 4d orbital. Half-filled 5d orbital. All right, so there you have it. Those are the exceptions. All right. One is an exception to promote it to a completely filled 3, 4, or 5d. And another one is an electron promoting itself, pumping itself up to promote to give you a half-filled 3d, or a half-filled 4D, or a half-filled 5D. So those are the exceptions. All right, so let's finish this one last problem, and then we'll be done with this chapter. And then whatever leftover time we have, we'll review for the exam. I think we got about 20 minutes, 30 minutes to go. All right. All right, so write the ground state electron configuration for phosphorus in P minus 3. So phosphorus. Where do we see phosphorus in the periodic table? Okay, that's 15. 15, so how will phosphorus be its electron configuration? So we have 15 electrons. Okay, 10 to go the way of neon, so that's neon. Okay, after neon, where will it go? 3s2, and then what? 3p1, 3p2, 3p3. Okay, so it's going to be neon, 3s2, 3p3. All right, that's how you do that. And what about p minus 3? What will that be? It would be, say it again? Nothing. Okay, p minus 3, what does that mean? Did it gain 3 electrons or lose 3 electrons? Huh? Gains. So what will it be? Three p6. So what is 3s2, 3p6? Argon. Okay. So these are isoelectric. Okay, isoelectric. Okay, P minus 3 and argon are isoelectric. Okay, and what does isoelectric mean? It means the same electron configuration. Okay. All right, so that is a wrap of this chapter. So we are done with that. 6 and 7 are in the books. Chapter 7 is in the books.